Today, let us take a look of the very last topic I want to discuss in the data structure, hash table. This is such an important data structure that links the data structure topic into database. And you will understand why this is such an important concept in terms of the database topic. In database, you know that we have a lot of different things that need to perform. More importantly, we need to be able to add the new record. We need to have the capability of the delete record. And we also want to find the record quickly by giving into the key attributes that I'm talking about. Think about this. Use the UCA student ID as an example. Whenever you go to an office, no matter it's chair's office, registrar office, financial office, what are they asking you for the very first information? It's not going to be your name. It's not going to be your other majors, school courses you take in. They would ask you for the very first thing is your student ID. That is considered as the key attribute to represent yourself, and then using that to find all related information. So if we are looking at adding a new record, you can indicating that we actually have a new student registered into the school, and we need to generate a new ID for the student, as well as all the spaces that are required to store the related information about the student. If a student is graduated, the school doesn't need to record that information anymore. Those information can be transformed into some other places, some other storage, so that in the situation that we need to delete the student's information from our active records, we would need to be able to do that. And not to mention, during the time that you study at the school, in any cases that you need to find your degree works, you need to find the courses you register, you want to generate a transcript, we need to be able to find your information quickly by looking into your key attribute. So how do we do this? We now, unlike binary heap, we only care about the smallest element so that we put that on top of the node and all the values are smaller than that one. This is not the case anymore because we need to be able to find whatever key that we generated in the process, and therefore we need to find a way to do so. Based on what you have learned so far, you can see that these are the student IDs numbers, and those are the names, GPA, whatever, etc. So that this key attribute is such an important. Saying that we have about 1,000 students we want to keep track of, and the student ID looks like this way. Pay a little bit details attention. You will see that this student ID number is actually a 7-digit in the example. And I also want you to think about your student ID for the UCA student account. How many digits is that? What does it look like? So if we want to do the insert, delete, and search, all of them doing quickly, we have several different ways to do so. Of course, the very first one is the unsorted array. So saying that whoever just joined the school, we just put them right next to each other. So that adding a new record would be easy because we can just simply add to the next available location. However, if we want to delete the target as well as to search the target, it would take a long time because you need to search one by one until you find that ID, and so that you can do the search operation or you can do the delete. In order to delete, obviously, you need to find the records that you want to do the deletion. If that is a sorted array, to do the search would be easy because it's sorted. We can use binary search, and that takes very small amount of resources to find it. However, in order to do a sorted array, if we want to insert someone or delete someone, it will take a while to do so because you need to do the shifting process. Saying that you want to add a new student in the middle, then every student IDs after that number has to be shifted into one place to the next location. For the delete, it would be the same thing, and we all know that shifting is not a good process because it takes time to do so. If that is a linked list, it would be easy to do the add as well as to do the delete somehow. To add a new item, we can easily add into whatever we wanted to add, just creating an additional space. So that's easy. Delete a target, it is fast at disposing the node. However, to find the node that you want to do the delete, it will take time, because if that is a linked list, you cannot use the binary search anymore because there is no index among them, and therefore you still need to search from the beginning of the node until you find it, and therefore the search operation will still take a big old notation of n, which is a linear operation. There are many more other more sophisticated data structures, such as the tree. We can do binary search tree because if we have a nice tree structure, the search process is not going to take too long. And then to do an insert or to do a delete, as long as the tree is in a more balanced structure, that can be performed in the log n process. However, you know that to maintain the balanced structure, it will take some time to do so. But you need to understand, so far, based on what we have discussed all the way from the beginning of the semester until now, binary search tree is probably the best choice that you have right now. However, of course, we want to discuss the last topic, which is the hash table that can handle these situations in probably the best performance that any other data structures can achieve. So what is hash table? What hash table, again, is based on the same concepts over here, saying that we have students, we have about 1,000 students, and the student ID numbers are 7-digit numbers. Saying that we have unlimited amount of resource. So the space or the hard drive or the memory is not a consideration. Then think about this. If we, to serve 1,000 students, saying that we have unlimited amount of resource, let us create an array that holds all possible spaces. Think about this. To create this, how many spaces need to be created? So saying that I am going to create an array, and you will understand this is going to be a two-dimensional array. So to create an array, what is the first index number that I'm going to provide? This is going to be 10 million, basically. You see, because it's a 7-digit number, the biggest number that can hold is 9999999. And if you also consider the index 0, you know that we need to create a two-dimensional space with the first index value equals to 10 million. First of all, you may think that's crazy, but think about how good can it be if we have that kind of luxury resources. If that is true, then their student ID does not need to be stored anywhere anymore, because the student ID numbers are exactly the index number. So saying that the Andy has a student ID 00123455, all I need to do is call the array, provide the student ID as the first index, and then whatever two-dimensional spaces indexes that I need to get, I can simply retrieve the second index. And by doing so, everything would be super fast. Because if you want to insert a new student, all you need to do is find an empty index, and we can easily put that there. If we want to do the deletion, we can find the index because we have the student ID. We can delete whatever that index point or what index location is going to be. And if you want to do the search, again, the index, the ID serves as the index. So doing so, this is the ultimate solution, because if we have that kind of resource, then doing insert, delete, and search, all of these requires big O of 1 operation. No matter how many students that you have, that can achieved easily. So when that is done, this is a representation of that concept. We will create a universe of the keys, all possible solutions. So in this case of the example we discussed, if we create the universe of keys equals to 10 million, versus that we have about 1,000 students, then you can see a lot of spaces are not mapped. So you can see that a lot of spaces are not mapped. And for the attributes or the key attributes that has been mapped, then we will be able to have some values that mapped over there. So those are the actual keys has been mapped, and there are some universe of the keys that are available over there. So by doing so, insert, delete, and search are all operated as the performance of big O of 1. And that's the best things can happen. But of course, it will take a lot of memory as well as the spaces. It is not really feasible to do that. So saying that if we want to find a compromise, having some way that instead of really creating that huge amount of space, if we have a way to map the student ID into a much smaller space. For example, if I have a hash function and we will be able to map this ID 001234 into a value of 134, and say that we have some hash function that we can map this value into 67. In other words, if we are able to limit those spaces into 1000, so after the hash function, everything will map into a much smaller value that's within the range of 0 to 999, and therefore all I need to do is I just need to create a space with 1000, which equals to the number of students that I have. And magically, this is the key part, magically, no two different keys map on the same number. So everyone will have their individual number. And by doing so, you see that all I need to do is I'm creating a much smaller space of the two-dimensional array. Whatever the ID maps, it will be able to map into a value, and that value will store the students' information over there. By doing so, we are actually get the best part out of two structures. One is the one that we create an unlimited amount of space, and on the other side, we limit the space that we have, and we might solve the problem. However, by doing so, it is still have all the good properties. We can add the element quickly, delete the element quickly, we can search the elements quickly, but it is of course very difficult to create a perfect hash function that maps all the keys into all different spaces. That's the key things that we want to discuss, because if we can do that, if we can create such a nice hash function, then we can save the space at the same time, create the best performance out of it. So what is this magical hash function? Hash function maps a key to an index with that winning in a range, and that range is basically the capable spaces that you are able to create, a reasonable amount of resources that you allocate. The desire of the property for this hash function is going to be simple and quickly. We can make it simple and we can make quickly to do the calculation, and you can also evenly distribute the values into the space that you are able to create, and then we would want to avoid what we call the collision as much as possible. So what is collision? A collision is indicating that for the same space, the same key, you have two different student IDs. After the hash function, ideally you will map into different values, but the collision is indicating you have two different students, but after the hash function, they are mapping on the same space. And that of course will cause some problems, because that's not something we were able to solve at this stage. So let's take a look of the simple example of the hash function, and then we can talk about the collision. So for the hash function, the easiest way is actually your mod operator, which is a good friend of ours. We use this mod operator many times in terms of the stack, in terms of the queue, circular queue. We also have all this appear in many different places. So again, the mod operator is try to get the remainder value. And that is actually the best way of doing the hash function, because whatever m is, that is equal to the space that we can create. If we can create, say, 1000 space, so we would have the key attribute mod 1000. So if the student's ID is 001234, after mod 1000, you will get 234. So no matter what value, large values that is, after the mod operator of this m, you will be able to limit the result into this value, m value. And m is equal to the spaces you are able to allocate. So that is the, and you know this is going to be fast. This is easy. You don't want to spend too much time creating some complicated hash function, and you will also delay your operation. And therefore, the final problem that we need to solve is what we call the collision. Once we have some simple enough hash function and it can distribute it evenly with the spaces into certain amount of range, the final problem is this. Saying that we have several values after the hash function, we get different values. However, you can take a look of this student 1 and student 2. They have different ID, obviously, but after the hash function, they actually map onto the same space. So what can we do if collision happens? And you need to understand, because we did not create 10 million spaces, it's totally unfeasible. Not to say 10 million. If I'm going to create 1 million for 1,000 students, that's already pretty expensive already. But since we are not creating 10 million spaces, no matter what, there is a possibility that we will find some collisions. And therefore, as long as we handle the collisions, we will be able to have the proper performances like we see earlier, insert, delete, and search all perform in the best way out of it, as long as we can handle the collision. So let's take a look of this. To solve the problem that collision generates, there are two major categories. The first one is hashing with the chaining. So what this is trying to do is that every hash table entry contains a pointer to a linked list of keys that hash in the same entry. That's the first way, create using linked list to create additional space, basically. The second one is hash with the open addressing. This is going to be the major focus that we want to discuss in this chapter. So what this is trying to do is this. Thinking about this, saying that I create 1 million space for 1,000 students. Of course, there are possible to have some collisions happens. When that happens, think about this. I have 1 million space and I only have 1,000 students. So that means there's still a lot of open spaces. So why don't I just use the other open space to store the collision problems? Say that I just store next to it, next to the original position I supposed to store. And we try to put some hint, or we try to leave some messages saying that, hey, you can probably look into the next location and the items you are looking may be stored right next to it. So that is the idea of using other spaces that are available to store the information. So let's start talking with the hash with chaining quickly, and then we will be able to focus on hash with open addressing. Hash with the chained method hash table is like this. Say now we create one array, one-dimensional array space. And then whatever values that are mapped into that location, we will create a linked list to store that information. So you can see that index 0, index 5, and this index has something mapped over there. However, for some reason, there are some students keep mapping into the space of 3, then what that's happening, then what we would do is that we use the same index location, and then we create the first student. When the collision happens, we use the linked list to create additional space chained with the first student. And if there's another student keep coming in, map into the index of 3, then we would be able to create one more space to hold the additional student. So this is the idea of using the linked list, and such an important topic that we have discussed throughout the semester, because we can quickly create some additional space to hold the information. So in this case, of course, as long as your hash function can evenly distribute the elements into different locations, this is actually a very good solution. Of course, if unfortunately you keep having some trouble, students are keep mapping into one or two indexes, then your linked list will go long, and that is the time you will slow down your performance. So this is the idea of using the linked list to help you solve the collision problem. So obviously by looking into this picture, you know the index of 1 has 2 collisions, index of 5 has like 3 collisions over here, but that's fine. As long as there's a collision, we use the linked list to help us create additional space and solving the problem. So this is the first choice that you may have to solving the problem. The second, for the chain hash table, a good hash function, it can do everything quickly. This is like what I've mentioned. Otherwise, if you have some values keep hashing into the same location, it will end up with a linked list method, and then adding an element is easy. However, to search or to delete a target would not be as easy as what we have seen. Therefore, the alternative approach is what we call the open addressing. So what we want to do is that we predefine a resource that we can handle, and we store all the keys in the hash table itself. Each slot contains either a value or null. And then when we want to search the value, we basically compute the hash function, and then we try to look into that space. This is what we call one probe. Of course, we may find the elements there, that's good. But if there is a collision, we then need to use the next available location. How do we find the next available location? That's a lot of studies over there. But try to use the imagination, just simply saying that, okay, if I find the location of 3 is not available, let me take a look of location 4. Maybe location 4 is available. So I would be able to look into the next available location. That's what we call another probe. So you will calculate how many times that you have tried. You would be able to find an open location for you to do that. So you can see that you can use the hash function and examine the slot of that location, and that's what we call a probing. If the slot h of k contains the value, the search is successful. If it contains null, then that means that's supposed to be there, and it's null, that indicating the value you want to search is not there. So it's an unsuccessful search. Of course, there's a possibility that you look into that location and it is not null, but it's not the value you are interested in. What that's trying to say is that then your value may be stored in the next available location. So you need to look into the next available location. And while you do that, you keep going that. Once you find it, you found it. However, if you keep going search for the next available location and you find a null value over there, that would tell you the value you try to search is not there. We would be able to look into many different approaches of what we call the probing. We will start with the easiest one, linear probing, which tells you to look into the next available location and next available location and next available location. And then we will be able to look into some more sophisticated, someone that's even what we call a double hashing, using 2 hash functions to guide you through the next available location. So that would be what I want to discuss for this video now. Then we will start looking into what we call the linear probing.